So in addition to the congruence postulates we've seen from triangles before, namely side, 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 and angle, there are two more that we can talk about that will allow us to show that two triangles are congruent. And those are AAS and HL. And both of these come from the idea that all we need to do to prove that two triangles are congruent is show that enough of their parts are congruent and in the right orientation so that the two triangles must be congruent too. And the first three that we saw, as we said, were side, 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 three congruent sides of one triangle, congruent to three sides of another triangle, and side, or angle, side, angle, both of which had either two angles or two sides and the included object of the other type being congruent to those objects in a second triangle. Well, angle, side tells us what happens if we have two angles and a side that is not included. So here, triangle ABC is congruent to triangle XYZ, but the side that we know is congruent is not included between the two angles. We don't know that XZ and AC are congruent. Instead, we know that YZ and BC are congruent. So the AAS postulate says if two angles and a non-included side of one triangle are congruent to two angles and the same relative non-included side of another triangle, then the triangles are congruent. The same non-included side is incredibly important here because the congruent side needs to be connected to the same angle in each of the triangles. AB corresponds to XY and YZ corresponds to BC. So if what we knew instead was that not that BC and X and YZ were congruent, but that BZ and XY were congruent, these two triangles then are not congruent because the side isn't connected to the same angle. AAS is incredibly particular about whether or not we have corresponding sides that are congruent. The angles, fine, but the sides that are congruent have to be connected to the same angle. So go ahead, pause the video, copy down the definition of AAS, basically this entire slide from the video. Come back when you're ready to see an example proof and move on to hypotenuse-leg. The same restrictions that we had on using SSS, SAS, and ASA are still there. In order to use AAS, we need to show that two angles are congruent and that a side not included between those two angles, but still in the same relative position of those between the angles in those two triangles are congruent to each other. So in this example here, if we go back to statements and reasons, here we're given that GK and GJ are congruent and that angle H and angle I are congruent. That's great. Those both go in the given. Here I'm going to write those down because those are incredibly important because they are parts of what we need to actually show that these two triangles are congruent. Parts of the given. And here we have a side and an angle. Now, what we also know between these two triangles, GHJ and GIK, we don't know anything else about any of the sides, but they both share this angle G, wherein GKI, we can see it is connected to we can see the GK is connected to that angle there, and in triangle GHJ, we can see that that angle is also connected to the side that we know is congruent. So we can say that angle G is congruent to angle G because there's only one angle there because of the reflexive property. Therefore, that angle connected to the side, that side not connected to the other angle, angle H and I, therefore we know that GHJ is congruent to triangle GIK by angle, side. Now, you might be wondering, is the same true if we have two sides and a non-included angle? To that, the answer is there is no swearing in geometry, meaning there is no SSA postulate. I will let you read into that how you will. But if we know two sides and an angle that is not included between those two sides are congruent, then no. We cannot say that the two triangles are congruent because there are multiple potential triangles there. The last of our congruence postulates is one that's specific for right triangles. Because we have that right angle there, there is something unique about right triangles and the setup. And that basically says if the hypotenuse and leg one right triangle are congruent to the hypotenuse and leg of another right triangle, then the two triangles themselves are congruent, and that's all we need specifically for right triangles. Go ahead, pause the video, copy down everything on the screen here, the statement of the HL postulate as well as the diagrams, come back when you're ready to see a proof of that, and then wrap up the video. So an example of this would be if we knew that LM and PN were congruent, we knew that LP was congruent to MN, so therefore it's a right angle there, and LM is congruent to MN, therefore it is a right angle up here. There are two right angles. Then we can prove that LP is congruent to MN. Well, using the givens, and I'm gonna cut a few corners here in the proof just for space reasons. Using the givens here, we know that LM is congruent to MP. That's the leg. And we know that because of the perpendicular lines, that we have some right triangles. The hypotenuse of both triangles is LN, which we know is congruent to itself because of the reflexive property. There is the hypotenuse, and therefore we know that triangle LMN is congruent to triangle NPL by hypotenuse leg. Now that we know that those triangles are congruent, we can say that those sides are congruent by CPCTC. So there it is. Those are actually all the ways that we can show the two triangles are congruent to each other using congruence postulates. So again, angle, side, if two angles and the same non-included side of one triangle are congruent to those pieces of another triangle, then the triangles are congruent. And there's no swearing in geometry, so side-side angle does not work unless we're in the case of right triangles for hypotenuse leg.